Okay, so let's have a look at some definitions of Bayesian games, and this will set up a structure that we can use to talk about equilibrium and to do some analysis of games where there's incomplete information. So what are the basic ingredients? The basic ingredients are fairly similar to what we had before, but we'll just also need to add some ways in which we can incorporate uncertainty. So what do we have? We have a finite set of players, say 1 through n. We have action sets, just as we did before. So each player has actions, A1, A2, and so forth, AN. We'll let A be the cross product again. And now what's going to allow us to incorporate uncertainty in terms of what players know about each other and what they know about the world is going to be through these types. So types is the word that's usually used, type sets. So each player will have a type set, and that'll encode what they know about the game, what the payoffs are, and so forth. And now payoffs, as a function of now payoffs will depend not only on what actions are chosen, but also on what the types are, and map into the real. So give us a number in terms of a payoff for player I as a function of what actions were chosen and what types every player were. So the utilities can actually depend, the payoffs can depend on everybody's type. And that's important in some of the examples. So for instance, in the conflict example, it was important. So in our conflict example, what did we have? We had 2 players. Each player had a choice of either fighting or not. What did the type sets look like? Well, the types for player 1, they were either strong or weak. Player 2 just had a single type. Doesn't matter what we call it. Let's just call it theta, little theta 2. So we'll use caps for the sets and little ones for the actual members of the set. So here, there's just one type of player 2. And the payoff functions then were given by the matrices. So player 2's payoff depended on whether or not player 1 was weak or strong. So what happened when they both fought depended on whether player 1 was weak or strong. So player 2's payoff depended on both types, as did player 1's payoffs. So in terms of uncertainty, we'll take theta to be a finite set for now. That will make our life much easier. And then we can talk about the beliefs of a given player as being a conditional probability distribution over the types of the other players. So when we look at a player I, particular player I, conditional on them being of type theta I, what's the probability that they assign to the other players being of type theta minus I? So again, this would specify the entries. If this is, say, player 1, this would specify what's the type of player 2, 3, 4, 5, and so forth. So all the players other than I. So this is the way in which we incorporate this. This is the reason that this setting is often termed Bayesian games and Bayesian equilibrium when we look at equilibrium notions, because this would often be derived from Bayes' rule. So if we specify a general probability over the different types that are in the game, then we can deduce what player 1 believes about other players, or what player I believes about other players, based on Bayes' rule. So generally this will be a conditional probability telling us what they believe about what other players are likely to be doing, and so forth in the game. So in particular, in our conflict example, player 1, the conditional distribution was degenerate. They always knew what was going on. But there we saw player 2 only had one type, and we encoded things. They had a p probability that player 1 was going to be strong, and a 1 minus p probability that player 1 was going to be weak. So there was a very simple structure in terms of what player 2's beliefs were, and that was encoded just in terms of this p and 1 minus p probability of player 1 being either weak or strong. Okay, just as we saw in that example, then a strategy in a Bayesian game now is going to be a plan of action for every player and each type of that player. So what should they do if they're of a given type? So it's a strategy for player I is going to be a mapping from their possible types into actions if we're talking about pure strategies. Or sometimes we'll actually talk also about mixed strategies, in which case we can instead think of this as mapping from types into mixed strategies. So they might be randomizing over the actions they're choosing. That's possible as well. So in general, we'll represent, we'll let S sub I of theta sub I be the actual action chosen by type theta I of player I. So in the conflict example, this was simply a choice of whether to fight or not to fight as a function of type. Okay, so now we have the basic structure, then we can talk about what the expected utility is. So if we specify a given profile of strategies, so this is S1 through Sn, so the strategies for each player, then for any given I and any type of that player, theta I, we can calculate what they think is going to happen in the game. So as a function of what they know, their type theta I, they have some probability distribution over the other players' types. So they assign a certain probability to the other players' types being theta minus I. Then we can say, okay, this is what they are planning to play in the game as a function of their type. This is what they expect the other players to be playing as a function of the strategies of the other players. Their payoff can depend on the types. And then in terms of taking expectations, they're just going to sum over all the possible theta minus i's, all the possible types that other players could give us. And this gives us an overall expected utility if these strategies are being played and the players of a given type in this game. Okay, with this in hand then, Bayesian-Nash equilibrium is easy to define. So it's going to be a profile of strategies, one for each player, such that this strategy for each type maximizes that player's expected utility given the strategies of the other player. So for each I and theta I, given the strategies S, we look at their expected utility from following the prescribed strategy, and that had better be at least as good as what they could get from any other action instead. So if they were of type theta I and instead they tried some other action AI, they should be getting at least as high utility from what's prescribed under the equilibrium strategies as not. So conceptually, this is the same as Nash equilibrium. It's just in a slightly more complicated environment where now we're specifying what they do as a function of their different types and their expectations of what other players are doing and so forth. So it's conceptually very simple, just a little more complicated in terms of the notation and the types entering into this calculation. Okay, so existence of equilibrium, that's always desirable to have some prediction of what's going to happen in a game, to at least have one equilibrium point. And if we have a finite number of pure actions available or finite number of pure strategies, a finite set of types, then if we are looking, if we allow for mixed strategies, then equilibrium exists. So this is actually can be proven as a corollary to Nash's theorem. It was proven by John Harsanyi in a set of papers where he really outlined Bayesian equilibrium in this definition, the set of definitions that we're working with here, in a set of papers in 1967 and late 67 and early 1968. And equilibrium, the arguments in terms of fixed point arguments and so forth to getting existence of equilibrium is effectively the same as what Nash outlined. It's just a slightly more complicated setting, but you can actually even move this into Nash's original setting by a clever reformulating of the game in terms of the normal form.